Okay, I guess I hope everybody's back. That's the problem with it. I can't really tell. Anyhow, we looked at layer 1 and
Here.
layer 2. Good. I mean, it's good to know somebody's there. Layer 1 and layer 2 uh, in these things. And error detection, layer 2, the frame format, remember, uh, it frames the data. That's going to be what we call a PDU, a protocol data unit. And each layer is going to have its own protocol data unit. Moving data around a network of networks, an internetwork between networks, is going to happen at layer 3, and the PDU here is going to be called a packet. Logical addressing between the networks. Each network is going to have its own set of addresses, and we're going to delve into IPv4 separately. So this is one of those, trust me, and it's going to get better. But logical addressing means that it can change. Where at layer 2, the address was permanent. It's a MAC address that's burned into the device at the factory. An IP address can change. Sometimes on a network, every time you log on to the network, you're going to get a different IP address. Cable modems tend to be persistent, and we'll talk about why that is when we get to that portion of it. When we talk about DHCP, which was one of the things that was listed alongside the applications in the in one of the earlier pictures. Routing has route discovery and path selection. Route discovery and depends upon, again, the protocol, how it determines the route path. So we have the route discovery, path selection to do these things, and once it defines the routes, the path selection, dependent again upon the protocol, it will pick the path that's best for it. The devices at the network layer are routers, layer 3 switches, and a basic firewall. Basic firewall, uh, we're going to filter at this layer and at the one above it at the transport layer. Uh, a layer 3 switch, different than a layer 2 switch. What a layer 3 switch, to me, in basic terms, is a router that works in hardware. A router is a device that works in software. So anything that works in hardware is probably, not probably, it's going to be a little bit quicker than something that works in software. The transport layer, uh, multiplexing and demultiplexing. Multiplexing is when we send multiple uh, messages over the same network. Put all the information together. Multiplexing, stereo FM radio, which you probably don't listen to anymore, but at one time was the big deal. Multiplexed, and it only had the same amount of bandwidth, the same amount of resource available that was in mono. So what they had to do is figure out how to put the right channel and left channel on, combine them, and then when it got to the receiver, it got demultiplexed, it got taken apart, and then we had stereo again. It packages the data in a stream of segments. And I've always thought of these segments as kind of like a roller coaster, maybe. And I'm also going to use that for time division multiplexing. But these things, and if you look at the way we run around in cars and in different things, the network, the data packets, I think can be uh, related to them. On the highway, we can talk about the bus, and when we're going to talk about duplexing one-way or two-way. Uh, can be think about an interstate or a one-way or a one-lane bridge. Port numbers allow the host to demultiplex and reassemble the data, and we'll talk about port numbers a little bit later. When we talk about TCP/IP, we'll talk about port numbers and how they become significant, why they are significant, what they mean to the whole system. Reliable delivery, they call it reliable and unreliable. The term that I personally prefer is connection-oriented and connectionless. What that means is connection established. Reliable delivery does acknowledgement. Somebody said they were in the Navy. And when you're in the Navy, you're in a mobile platform. And when you try to get mail, sometimes they can find you and sometimes they can't find you. What I would do on deployment was I would number the letters so that if they got to my wife out of sequence, then she would know why, what was the content didn't make any sense. So what this does, segmentation and sequencing, is it numbers each of the packets as it goes out so that when it gets to the other end, it can get reconstructed into the correct sequence. And it also acknowledges the receipt of the packet, kind of like if you return receipt required sort of thing, you get an acknowledgement of the package when we go through these things. Segmentation segments them and sequences them, puts them in sequence, and there is flow control here so that you don't overload the other resource. Sometimes you get a brand new machine, brand new really fast machine connected to a not really fast old machine like I use in most cases. And the really new fast machine can overload the old machine, and that's what flow control is all about. If you start getting too much data, it sends what we commonly call a choke packet that says slow down, slow down. Don't send the data so fast. The devices at this thing are multi-layer switches and security appliances at the transport layer. The upper layers that is less important in the real world. What we're talking about from the transport layer back down is what we're going to manage in networking. This part of it's kind of like is beyond the router, which is where we're going to control information. So the session layer identifies the sequences of messages. It sets up the conversation and it tears down the conversation. The dialogue control, simplex, half duplex, and full duplex. Simplex is kind of like a broadcast. It just sends information. Half duplex means that we can transmit and receive, but we can only do one at the same time. One at the same time. Do one at a time. A duplex, we can transmit and receive. We can do both of them at the same time. Half duplex would be like a walkie-talkie, CB radio, something like that, where you talk and somebody receives, and then when they get the message, then they talk and you receive. Full duplex like a telephone, because you can talk while somebody else is talking on the telephone. The presentation's a character set, compression, decompression, encryption, and decryption. Kind of, sort of, it's not the kind of encryption that we're talking about today in the world where we encrypt data and when we encrypt conversation with IP security, where we actually use a separate process in order to encrypt the data. The character set conversion is we have to have the same data to go from one to the other, otherwise it won't recognize it. If we're going to a web page, we have to send an HTTP to an HTTP, and it's checking to be sure that the information is right. Maybe a simpler way to do this, if you send a Word document, you got to be able to read a Word document. The application layer, application programming interfaces for software programs can be written for any layer. APIs can be written for any layer, but the application layer, what we're talking about here are things like web servers or email servers or FTP servers. We're not talking about Microsoft Word or Excel are not the things that are going to be there. PDUs, the protocol data units at each of these layers, and sometimes sometimes you get asked things like this and sometimes you don't. So we have segments, packets, frames, and bits. At the upper layers, the upper three layers, we have data, and my mnemonic is don't some people fight back for this one, so that you can hopefully help you remember these things. The OSI Model Summary here, application presentation, the applications, web, and all those things, stateful application layer, security appliance, and that shouldn't mean anything to you yet. That's in firewalls. We have stateful and stateless firewalls. Multi-layer switches, the transport segment, the datagram here, IP addressing, the basic firewall, the router is going to be the device. The data link frame, the MAC address, EUI, which we will discuss when we talk about addressing at layer 2. A bridge and a switch are the devices here, and the physical layer, transceiver, cable, media converter, and hubs work at that layer. So we've talked about star mesh, bus, ring, point-to-point, hybrid, peer-to-peer. We talked a little bit about protocols, and then we talked about the topologies, and we described the functions of the layers of the OSI model. What this thing now has, and let's see how we do here. What term is used to describe a topology in which computers act as both clients and servers? Feel free to chime in and answer. You don't want me to have to start this all over, do you?
Peer-to-peer.
Peer-to-peer. Thank you. I knew you didn't want me to start it all over. What is the characteristic of bandwidth of the bus topology? And I think I probably didn't say that explicitly, but it's shared between all the nodes connected to the bus. And that's going to slow things down also.
Is that called shared access?
Yeah, it would be shared access. Yes, carrier sense multiple access, collision detection. What type of device is used to implement a star topology?
Switch.
Switch, also a hub, and a router can also do that. Although I don't think it was explicitly stated that a router did, but a router can. You need operations to continue if one link fails. How many links do you need to connect 3 sites? N times n minus 1 over 2. 3 times 2 over 2.
I said 3. I was muted 3.
You're exactly right.
Oh yeah.
But if you look at 4, it really goes up significantly because that's 12.6. If you just do it's not really tough arithmetic, but if you look at it, as you get more than 3 or 4 devices, it's really a lot of connections. And it becomes really difficult to make those things. There are some protocols as you get into routers that make it easier to do, but you still got to pay for all those connections, so it's going to get relatively expensive to do something like that. In which sublayer of the OSI model do network adapter cards operate? Sublayer. It's going to be layer 2, but they say the MAC sublayer. Or data link sublayer. The MAC is the thing that gets there.
Data link.
Yeah, physical.
Say again, Tamika?
I was going to say physical address.
Yes.
Okay.
Which component is responsible for translating the computer's digital signals into electrical or optical signals on the network cable? That's a toughie, huh? The device is a transceiver, and I may not have said that clearly enough, but the NIC is a transceiver, a transmitter receiver that sends a signal and receives a signal. We think about electrical signals and wireless, but not really that much on wired, but it's an electrical signal that transmits and receives also. True or false, the session layer is responsible for passing data to the network layer at the lower bound and the presentation layer at the upper bound. Gotta go back to the model for that. Let's see if we can get back to the model. So it said the session layer. So the session layer is going to pass it to the transport layer at the lower bound and the presentation layer at the upper bound.
So that's true.
No, it's let's go. Let me go back and read it again, because it says that it presentation at the upper layer, but network at the lower layer, and that's the kind of things that they'll do
Oh,
to.
okay.
That's the kind of layer they'll do. The things they'll do to you is give you a half truth. One of the things, and I'll try to address things as they come up on my mind about testing, is a lot of times you can answer as many questions by what the answer isn't as by what the answer is, because you can eliminate a lot of things, and don't be afraid to limit. Throw them all out that aren't true. They'll say that's not true, that's not true, that's not true. Sometimes you'll come to that's the only thing left, huh?
Presentation is above the.
Yes, presentation is the transport.
So you're saying it's true.
Transportation is below it. No, it was false.
It's false because it's the presentation layer is that portion is correct. The network layer portion is wrong.
That's all. Yeah. Networking is the third layer, right?
Right. Yep.
Yeah.
Which OSI layer handles the concept of logical addressing?
Is that the internet?
Network, internet or network. Yep. Depending on which model you're using. Which layer is the port number introduced? And that's the transport layer. I think I said that, but we'll get into port numbers as we get there. The OSI, which two OSI layers define how multiple computers can simultaneously use the network media without interfering with each other? And that goes back to the TC. That goes back to the network access layer. So what we do is combine the two lower layers. Let me see if I can get back to that one. Right here, went too far. This one combines, this is the one that combines the two lower layers. So we're going to have CSMA CD at the data link layer, and then the physical, all this stuff works together. They defined a NIC for years as a layer 2 device, and then it's like, well, you know, it's both devices. And then they say, well, maybe it's a layer 1 device. It's a both devices. And that's why this model works better, because it combines them and makes it a little more realistic as to how the two layers work.
So what was the question again?
Which two layers, let's get there. I gotta get back to it. There are my notes here. Which two OSI layers define how multiple computers can simultaneously use the network media without interfering with each other? And this actually ought to say on a bus, because if we're on a switch, not a big deal.
But it said without interfering with each other.
Without interfering with each other, yeah. The carrier sense, multiple access, collision detection. You listen to the NIC listens to the media to be sure nobody else is transmitting, and that's what this is all about. And then it sends its information. And that's what happens in the data link in the physical layer. Is that making any sense?
Yes, it does. No,
okay.
Yes.
I said I'm behind, but I want to try to show this little thing anyway. I've got a little, I tried to convert this thing and it wouldn't convert. I've got a little flash thing. Let me move it over here if I can find it. Oh, I know why that won't go. Here we are. All I have to do is take my headset off, and because
In this presentation, you will see how the Open Systems Interconnection Reference Model, or OSI model, describes the process by which data is sent over a network. The OSI model is divided into 7 layers. Each layer represents a different stage in the process of preparing data for transmission over a network. The process starts with the application layer on the sending host, where applications are connected to networking software. The data to be sent is put into a packet that passes down through each layer, accumulating routing and tracking information until it reaches the physical layer, where it is sent out over the network to its destination. You follow a similar process when you send a letter. Here is an example of the similarities between the functions at each layer of the OSI model and the process of a letter being sent by a private delivery service. You start the process by creating a document and sending it through interoffice mail to a translator. The interoffice mail represents the application layer of the OSI model where the connection between an application and the network software is made. The next stage is the presentation layer, where your text is translated into the recipient's language. In the OSI model, the source and destination clients choose a common communication syntax at this layer. Next, your document goes to the mailroom, where the destination address is checked to make sure that the service delivers to that area, and then your document is put into an envelope. This is similar to the session layer of the OSI model, where the connection is made between the sending and receiving clients. If you ask for guaranteed delivery of your letter, a tracking number is assigned to it. In the OSI model, the transport layer is where a reliable or unreliable protocol is chosen. The address is then added to the envelope. In the OSI model, the network layer is where the destination address is added to the packet. The next step is where a secure seal is applied to the envelope and the type of transportation is chosen. In the OSI model, the data link layer is where the packet is put into the correct format for transmission. The physical layer is the last stage. The envelope is put on an airplane and taken to its destination. This is similar to putting the packet onto the network cable at the physical layer of the OSI model. When you put the 7 stages together, you have the 7 layers of the OSI model. Applied to a network, the OSI model defines the following functions. At the application layer, network access is provided to applications such as the ability of your word processor to load files from a server or to send a document to a print device. At the presentation layer, the client computers that are communicating with each other choose the best syntax that they have in common. At the session layer, protocols maintain the connection between the communicating clients. At the transport layer, either a reliable or unreliable protocol is chosen to make the connection to the recipient, depending on which type is needed by the communicating clients. At the network layer, the destination address is added to each packet. Also, when a reliable connection is made at the transport layer, protocols at the network layer do the tracking and checking needed to ensure the connection's reliability. At the data link layer, the packet that has been assembled at the previous layers is prepared for transmission over the networking hardware. At the physical layer, information about the networking hardware is used to send the packet out onto the network. The process works in the opposite way on the client that receives the packet. As it goes up through the layers, the information that was attached to the packet before it was sent is checked and removed at the same layers on the receiving host. When it reaches the application layer, only the original data remains. A phrase that may help you remember the order of the OSI layers is, all people seem to need data processing. In this presentation, you have seen how the OSI model describes the process by which data is prepared and sent over a network.
Hopefully you could hear that. I thought that was a pretty reasonable comparison to.
Yeah, that works for me. I'm a visual person, so that I understood that better.
Well, I'm going to do it. I didn't get a chance today. I'm going to do a because I couldn't upload this one. It's wrong. It's a flash file, and it won't let me put it up into the share. And I said there's some documents there to share. I'm going to get a Dropbox share set up, or a box share or something, so that I can put these things that they won't allow me to upload like that in there, and you can watch them on your own.
Okay. Okay, cool.
Yeah, that'd be nice.
Yes.
Let's see. I got to find out where I am. We got one more unit to do tonight. I know you're thrilled, but we're getting there. Is this making sense? I always ask this question. If it's not, we have to start over.
It's coming together. What pages are we coming from? I mean, like, because the book that I have, I'm trying to find out
Oh, you
what
said you
page.
had the paper one, didn't you?
Yes, sir.
The ebook, the page numbers are over here on the page numbers that it's on are over here on the slides. It should be unit with the topologies and OSI should be unit 1, and the when we're getting ready to do Ethernet should be unit 2 and module 1. It should be. We should have started at the beginning of the book. I said I've got the ebook, and
Yeah, on the ebook, the numbers are at the bottom of the screen,
yeah,
but the page numbers are actually at the lower right hand corner.
yeah,
So
yeah,
you can see like page 27, so forth.
yeah, yeah.
Okay, let me look.
So this one maybe I've already covered. Hopefully some of what we're going to do here, but understand the properties of transmission media, data signaling, media access control. That's the CSMA-CD or token passing, and that's basically what we have. The features of 802.3 Ethernet, and I used to love to ask what makes an Ethernet, and it's CSMA-CD and it's a bus topology. That's the primary characteristics of an Ethernet. The properties of MAC addressing and ARP address resolution protocol. They kind of mix some of the protocols and some of the stuff in. I think I've got I told you, and that's a good one to look at. I've got a capture. Maybe if I've got enough horsepower to run this and my Wireshark at the same time, then we can look at what an ARP packet actually looks like and what the header looks like when you get it into an analyzer, a network analyzer, or not an analyzer, but a protocol analyzer. The use of packet sniffers, protocol analyzers to capture and examine network traffic, and those are the things that are going to be very useful to you for both troubleshooting and as you go on. Many of you said you're going on to security. As you look at stuff on the network in the security area, you're going to use these things. So bounded and unbounded, I think I've used those terms before. Bounded media, fiber, and copper, something that has kind of an insulation on it, I guess. Maybe it's bounded. Wireless media is unbounded. Unbounded can go anywhere. And we talk about bandwidth, and bandwidth means a couple of different things. Channel bandwidth. It's a range of frequencies. A radio station has a lower end and the top end, and then you tune to that channel and they put their data inside it. Channel capacity is in hertz or megahertz. And the greater the range, the more the data. And we have baseband and broadband. Broadband, I'm using broadband tonight because I have cable modem. Broadband means that I have a lot of different channels stuffed into that single cable, because in the cable modem, in the cable itself, you get 150 channels with nothing to watch through the same piece of media. The networking works at a different frequency than everything else. That's why it can get, and they continue to make them faster and faster and faster. Baseband, this coax that we've been talking about on the bus, and the twisted pair, which is the wire that's going to plug into the switches and the hubs, are going to be baseband. That means that they only have a single frequency, and everything operates at that single frequency. The thing we're really concerned about is data rate. When I go to check my bandwidth, I call it my bandwidth. It says that I have, 6 meg up and 25 or 30 meg or whatever it is down. That's actually going to be my data rate, how much data I can actually send on these things. Baud versus bit rate. a baud is actually the changes per unit time, kind of based on frequency. And at one time, I think 14,400 was the maximum baud rate. It's gone up now. It got 119,000 for baud rate, but that's still not going to get us the 30 megabits per second that we get for cable modem. The bit rate is how much data can actually go across this thing, and we get that by encoding and multiplexing the way they do those. Transmission media, one of the interferences, many of the interferences with it are attenuation and noise is unwidened signal. Attenuation means that the farther the signal goes down the wire, the lower its intensity. It drops off. It's kind of like if you were coming down a mountain in your car and you ran out of gas, and we'll assume that your power steering still worked, and you get on a flat, the farther you go, the slower you get. So the farther you go, the lower the power of the signal gets. And at some point, we're going to have all sorts of noises around everywhere in different environments. Obviously going to have a lot more noise in other environments. But if the signal gets to where it's lower than the noise, then we're not going to be able to repeat it. One of the devices that we have at layer 1 is a repeater. It's not an amplifier, it's a repeater. It actually rebuilds the entire signal. If it were an amplifier, it would amplify everything, including the noise. So a repeater, and hubs and switches are also repeaters, as are the MAUs, the mouths for the token ring. So each of these devices renew the signal as it gets to them. And we can use them to increase the distance that we want our signal to go. Copper cable, electrical signals, we have twisted pair and coax. And these are subject to high attenuation and interference just because they're copper. They kind of act like a little bit like antennas. And they have impedance in them, and they can leak in and leak out. You can actually, if you're good enough, and I'm not, you can actually, and you don't have shielded cable, you can, if you're close enough, actually receive the network signal off of the cable. In the, I guess it was the 80s, the government built Tempest, and I think they talk about Tempest later on in the book. Tempest, which were shielded computers, because I am told, I never did it, never saw it, but I'm told that if you didn't have a Tempest machine, that you could, with not a whole lot of material, build a device that would actually receive the image from the screen. So all of those things become real issues. High attenuation, loss of signal as we go longer distances, and we're going to find out that when we get into the twisted pair, they don't go really very far. They go 100 meters. We're going to have that again in a minute, but these are the kind of the numbers that you're going to have to remember. The coax, 10 base 2 and 10 base 5 are going to be the coaxes. The 10 base 2, for whatever reason, is 185 meters, and the 10 base 5 is 500 meters. What you're generally going to find at hubs and switches, the distance they're going to go, and when I try to memorize these things, I try to memorize the exceptions to the standards, and then and everything else is going to be whatever the standard is. And the standard for hubs and switches and twisted pair is going to be right around 100 meters. Fiber light signals, less susceptible to attenuation. It can go a lot farther, and less susceptible, like not susceptible to electronic or electromagnetic or RF radio frequency interference, because it's light. Higher bandwidth over longer distances. You can go longer distances because you don't have the interference and as much attenuation. So you can have a very low signal before you have to repeat it, because you don't have the electrical noise that's going to be in the copper cable. It's also more expensive to install. The fiber itself has come down in price quite a bit, but the connectors are still pretty expensive, and the process to put them on, to inspect and to build the devices is pretty expensive. We had a fiber microscope, and I looked up the price of those things, like somewhere between $5,000 and $10,000. So not the fiber itself, but everything that goes along with it becomes relatively expensive. And then we have wireless radio frequencies, and these are unregulated bands. Unregulated means anybody can use them. And they're the 2.4 megahertz gives you a longer range. The 5 gigahertz is going to have a higher data rate. When they started building these things, both of these were competing in the early days. What happened was the 5 gigahertz actually probably was better, was more secure, higher data rate, all sorts of things, but they ran out of the silicon to actually build the chip. So the 2.4, which are our B, G, and N standards, took over the wireless. There is a limit on power on these things, even though it's unregulated. So we have limited range, and the range, as those of you with wireless, you can walk around your house and get a wireless detector for your phone and figure out how far your wireless goes and how many other wirelesses are in the area. I was sitting down the other night and looked at one, and there must have been 20 of them because there's a whole bunch of houses behind us. There must have been 20 networks in the area. They are susceptible to interference and jamming. Lots of things in the unregulated frequency. Jamming, for instance, your microwave works at the same frequency, or the microwave may jam it. Wireless controllers, game controllers, will go on and on and on and on and on. I had a student one time say, my wireless doesn't really work very well. I'm having problems with it. So where is it? He said, it's on top of my refrigerator under a fluorescent light. Well, yeah, it's going to get a lot of interference with it. And he did get a lot of interference with it. Digital signaling. We have digital waveforms, which are discrete. Really, and these show these really nice and clean. They really don't. They kind of come up like this and go down like that. But they're not analog, and down here is an analog signal, but we want to do everything in digital signaling into discrete pulses. It's typical of baseband, uses the whole bandwidth. We can turn an analog signal into a digital signal by sampling it, and the higher the sample rate, the higher the quality. Also, the bigger the file is going to be. So you can turn analog into digital by sampling the information. And the Nyquist theorem, I got it over here, says that your sample rate is twice the bandwidth. And an example is a human voice is generally considered to be 4,000 hertz, 4K hertz. So we sample it at 8 kHz for an accurate representation of the voice. The sample size is 1 byte, 8 bits. So 8 kHz times 8 bits is 64 kilobits. The higher the sample rate, the bigger the file's going to be. Analog signaling, continuous, these are the things that you see a lot of different waveforms. The voice waveforms, radio stations generally, although we do some digital transmissions now with a satellite radio, but over the air probably going to be an analog form, a continuous waveform that goes from point to point. Modulation encodes information on the carrier, and I'll do a really poor rendition of that. We'll put information on the carrier here. The carrier frequency is what you tune to. If you tune to FM 104, 104 megahertz is going to be the carrier, and then you put the modulation around that frequency, on that, around and through that frequency. The properties, the wavelength is how long it is here. The wavelength, The frequency is how many times it goes up and down per unit time. The amplitude is how high we go, and the phase is where we start. We're going to, when we get into some of the ways that we put more information on, we can start these things and have phase modulators. We'll put two signals at different phases on this thing. Inefficient and susceptible to noise. And nobody listens to AM radio. I don't even do that anymore, but if you drive under a power line on AM radio, you get susceptible here, and that's because it's amplitude modulated, frequency modulated, that you can chop the noise off on the FM radio. Multiplexing and demultiplexing, combine multiple sources of information for transport. These are a couple of things that I went out and got. We got frequency division multiplexing. We have A bandwidth, A channel, and we got multiple frequencies in here. This would be kind of like, these wouldn't be the frequencies, but it would be kind of like the way you get cable TV delivered to you, because each of the channels is on a different frequency, but they're all in a broader range. And then we have time division multiplexing, and this one, each time component gets so much of whatever. And in this one, A has 4 bits of data, and we have A goes 4 times in here. There's A and A and A. And then B gets to send some data. It's only going to have 2 of them, so B is here and here, and C only has 1, wherever it is. There's C. And D has 3 of them, which are D. So we have time division multiplexing on these things. These channels can use the full bandwidth when we do these, when we do the frequency division multiplexing. Contention, we talked about contention, collision domain. Collision domain means that we can have collisions, and one of the ways to think about this is, let's put all you guys, actually, first of all, let's put 2 of you in cars and put you in a parking lot, or maybe even put you on a highway and blindfold you. How's that? What's the chances that you're going to have a collision? Probably pretty good. What these things do, the bus and the hub are all a collision domain, a single collision domain. And that's what slows them down quite a bit, because you have to wait, and then you have collisions, and the more devices you get on the bus, the more likely you are to have a collision. So that carrier sense, we listen. Multiple access, we have a whole bunch of things connected to the same bus. And then once there's no signal, nobody else is sending information, we send our data. And then we listen to see if there's a collision detection, and if there is a collision, do a random back off and start all over again. Collision avoidance is what wireless uses, and it kind of slows wireless down, because what happens is that the wireless NIC has to request permission to send, and then it gets permission to send, and it sends the data, and it goes through that process over and over and over and again. Switched networks don't have this problem up here. A switched network creates a dedicated path, and we'll go through here. A dedicated path, and it is full duplex. It's like an interstate, not like a 1-lane highway that we have up here, that you have to get, you can only do one thing at a time. On this one, we can transmit and receive at the same time. Half and full duplex. Half duplex, we can transmit and we can receive, but we can only do one at a time. Full duplex, we can transmit and receive at the same time. Here we can transmit or receive, And down here we can do both at the same time. Switches are going to be full duplex, and they're probably going to be 100 meg or gig, or we're getting into 10 gig world now, but it's still pretty expensive. So again, back to what I said earlier, if I was going to do one thing to make my network better, it would be put a switch into it. Communications, unicast, broadcast, and multicast. Unicast is one computer to the other, a one-to-one relationship. A broadcast, we send something to all the computers, and in the IP world, it's going to be all the computers on an IP network. A multicast, you actually sign up for a multicast, and you get the information, but only because you ask for it. Actually, the computer signs up for the multicast. Broadcast domains. Routers stop broadcast domains. Broadcast domains are something that are going to happen at layer 3. Broadcast domains are going to be at layer 3 of the OSI model. And a broadcast is sent to, and it's already got the red here, is sent to every computer on that side of the router. Routers do not pass broadcast. They don't go through them, and that's one of the things that they stop. Separate broadcast domain over here. The broadcasts from this network don't go to the other network. Broadcasts are something that can generate a lot of traffic on a network if you have a lot of broadcasts, and if you do any traffic analysis on a Windows system, you're going to find it does a lot of broadcasts. Ethernet frames, the principal wire technology. We've talked about this a little bit. We talked about the MAC address, and this is what this is here. It's a 48-bit, a 6-byte destination and source MAC control address. The frame length and maximum transmission units, the MTUs are going to be somewhere around 1,500 bytes. Frame types, we have different frame types in Ethernet. And in the header, and we've said header, but in the header we got the destination MAC. We looked at this before. The source MAC, the length or type, what kind of Ethernet is it? The payload. A CRC is a cyclical redundancy check. What it does is it creates a number based upon an algorithm and what the content of the frame is. And when it gets to the other end, it recreates the CRC, compares the two, and if they're the same, it's okay. If it's not, it kind of throws it away. This one doesn't have any retransmission or error correction. It has some error detection, and that's what this CRC does. It does some error detection. The retransmission is done at the transport layer. That's what that reliable they talked about. Virtual VLANs, they stuck it in here. We've talked about LANs. What a VLAN does is if let me make another bad drawing here. If we had a switch, and VLAN is something that we can do in switches, and we have our ports, and I'll just do little dashes for ports. We could go out and create a physical network and connect them to a switch. What a virtual local area network does is allows us to divide the switch into different networks. And if we do that, we're going to have a router in here. Can't spell it. Can't write it. Router to connect the different VLANs, because these are virtual, but they are actually still LAN, separate networks. The advantage to a VLAN is we could have a VLAN 1, or say 3, we don't use 1, and 5, and we could have another switch over here and connect them together, and we could have different physical locations and put them on the same network, 3 and 5. And that's what this tagging is all about, this 802.1q, this tag here. when it goes, and we're going to have a special port called a trunk that allows all the traffic on it. It sends the traffic from VLANs 3 and 5, and if we have traffic on 5, it gets a tag that says, hey, I'm VLAN 5. When it gets here, it's actually stripped out when it comes into the switch, and the switch sends it to VLAN 5, and none of the traffic goes to VLAN 3. So we can have virtual local area networks using switches and using Ethernet, if that makes sense. The legacy Ethernet standards here, 10 base X. When we do these things, what each of these things mean: 10's the speed, 10 megabits per second. Base is baseband, not broadband. And X is going to be the distance. We'd have 10 base 2, which means that it's 145 meters, 185 meters, 145 meters, 185 meters. Which what it says right there, 185 meters. 10 base 2 thin net is different from 10 base 5, which is called thick net. 185 meters, maybe you want to go farther. There's a physical bus and a logical bus. It uses the 5-4-3 rule, which says we can have 5 segments, 5 different segments, separated by 4 repeaters, and 3 of those segments can be populated. So we have 185 meters, a repeater, 185 meters, repeater. I should have put my bus in here first, and then a repeater, and a repeater. So we have 1, 2, 3, 4. We've extended this to 1, 2, 3, 4, 5 segments times 185 meters. So it really goes a little bit longer. The reason we have these length restrictions is there's a rule that the leading edge of a packet has to reach the farthest extreme of the network before the last part of the packet leaves the device, so that you can detect collisions. Each of them is going to be different. The 10 base 2, 185, 10 base 5, which is called thick net, is 500 meters. 10 base T, again 10, and we could have 100. 10 megabits per second baseband. T is for twisted pair. Twisted pair, and the maximum cable segment is 100 meters. The minimum cable length is a half a meter. You have to have at least 1.5 feet. Or you get into the electronics, and our double E can talk about that, that'll actually block it. The maximum number of hubs between nodes is 4, so we can have 4 hubs, which is kind of like the 4 repeaters that we had in this thing. On fast Ethernet, you can only have, and we'll get that in a second, in fast Ethernet you can only have 2 hubs. 100 base X fast Ethernet, 100 megabits per second. TX twisted pair, FX is fiber, F for fiber. Hubs and bridges are increasingly replaced by switches. I think that hubs and switches are increasingly being installed. Auto negotiation of link properties. What that means is that it can be set up to auto negotiate speed, so that if we happen to plug in a 10 megabit per second NIC into it, it would automatically negotiate it down to 10 megabits per second. And if you have it set for 100 and you plug a 10 into it and it can't auto negotiate, then it's not going to communicate. 100 meters for fast Ethernet, 100 base FX. MMF is multi-mode fiber. We have single mode fiber, 412 meters or 2,000 meters for full duplex, half duplex, and full duplex. 1,300 nanometers is how big it is. 62.5 and 125 is the core size of the fiber. Gigabit, mainstream technology, twisted pair. Same thing, we get the baseband, the T's, the TX's, 100 meters, For unshielded twisted pair, Cat 5e and Cat 6. Fiber, a little bit different, 225, 150. 1000 base LX. Single mode fiber can go 5 kilometers before 3.1 miles before it's repeated. Fiber goes a lot farther, but it doesn't go to infinity. 10 gigabit is very expensive compared to everything else, but it's just like gigabit was very expensive when it first came into existence also. Let's see where I am here, how far we got to go. Because I want to do one lab tonight. I'll tell you what, why don't we take 10 minutes again, unless you just want to keep going. 10 minutes okay now? Trying to do this on the hour. Nobody wants a break?
Yeah, that'd be fun.
Let's take a break.
Yeah, that's fine.
Can you hear me? So this one's just
back. We're in the home stretch now. The MAC addressing is layer 2. It has, it's called, I refer to it as the extended unique identifier. What it has is an organizational unit identifier. The addresses are written in hexadecimal, like this. And the first half of the address is the organization. This is the OUI, the organizational unit identifier. The second half is the serial number, and these have to be unique. We talk about local administered addresses here. You can do that, but you got to be sure that they're unique. Let's say if you want to have them on a particular network or whatever. Don't know that that's going to be anything that you really want to do, because they come unique, and if they're not unique, they will totally destroy your communication. Having done that accidentally in a virtual machine before, got a bunch of machines that had the same MAC address. Sometimes it'd work, sometimes it wouldn't, sometimes it'd go one place, sometimes it'd go the other place. They have to know, they have to be unique, because this address is what uniquely identifies the node. Everyone has a unique address. And you can look these things up on the internet if you really care about which are which. Whenever, we'll go over here, to jump over here to this, because this shows up in, this is a Wireshark. I'm going to show you a capture here in a second that I did. But it shows up in the MAC address. It actually interprets the organization for you. Individual, the IG bits are down here. If you have a group address, locally administered address, globally unique address, individual address. So a 1 or a 0 is going to dictate what goes on here. Unicast and broadcast, and we talked about those. Unicast goes computer to computer. In a shared Ethernet, the data actually goes to, my pen on, goes to everybody. We're going to make it go this way. But it's only accepted by the machine that has the correct address. This one, actually, I'm going the wrong way. The destination is, and we'll look at it, is 1111. Here we got the source. They got it backwards because the destination was first, wasn't it? And the destination is 1111, which is this guy up here. He takes it. The rest of them see it, but they don't accept it. Now, when we start running sniffers, we're going to put the NIC into what's called promiscuous mode. And when we do that, it actually looks at everything that's on the network. And this one up here with the broadcast traffic, we send broadcasts to everyone, and the destination address is all F's, and this is going to be a hardware broadcast address. So it goes to all of the stations, and they all accept the broadcast. So a broadcast, don't know that it'll come up again, but a broadcast is all F's. In this case, 1, 2, 3, 4, a whole bunch of F's, right? How many would it be? 4, 8, 12. And that's right. Because each F represents 4 bits, and we have 12 of them. 4 times 12 is 48. We get our 48-bit address. I love it when a plan comes together. Local address resolution, and we'll do remote address. This is kind of the communication process. If a sending host, we have IP addresses, which we haven't addressed yet, but we will tomorrow, and MAC addresses. The IP are the logical addresses, the MAC are the fixed addresses. If we want to go to the source, the destination, who has 10, tell this guy. If we want to go to 10.0.0.11, this host over here, and we don't have it in our what's called an ARP table, if it's not cached, then we send a broadcast to all stations that says, hey, tell me who has 10.0.0.11, tell 10.0.0.22. So it sends its MAC address back so that we can associate the IP address with the MAC address in our computer, and we know where to send it to, because back to the thing that I've said a couple times, the address that gets the information to the individual computer is the layer 2 address, the MAC address. The IP address simply gets it to the network, gets it to the correct side of the router, which was not shown here. If we have a remote address, first it determines that it's not on the same network, and then it goes to the router, the default gateway, and says, give me your, because it knows the IP address of the default gateway. Who has 10.0.0.254, which is the router? Tell me. And then it sends its traffic to the router. The router goes through the same process with the MAC address. It doesn't change the IP address because we have to know where to come back to. The MAC address just goes from device to device on down the line. And it goes to the MAC resolution every time unless it's in the cache. And if you want to see the cache, you can go to a command prompt on your window and type ARP space -A on a Windows machine. The ARP cache, the ARP utility, here it is. We got there just in time. ARP-AG, different views, the MAC address lookups, and they say that Wireshark, and you can go to Wireshark and do an OIU lookup. Wireshark's not the only one. Wireshark is a sniffer. It's a pack. We can capture packets and protocol analyzers. It's free. If you haven't used it, I'd recommend you get it, install it, play with it. Capture packets, see what they look like as you go down the line. I told you that I would, and I've got it here since I finally got so much stuff open on this thing. See if I can drag it over here. This is a packet capture. If I can. I did earlier today. And this is ARP, what it just said. What it just said, this goes from a Samsung, and these are devices, and I have no, oh yeah, this would be a tablet on the network. Who has 192.168.100.1, which is the router? Tell 192.168.100.63, which is going to be this guy. And we talk about the identifying it. This identified the organization as Samsung, and then the second half of it is going to be the unique part of it. And then we have a source is a Dell, and the Hisense is a television. So the Samsung went to the broadcast. We go through these things again. ARP, who has, and then we'll go down here into the frames themselves. Look at them a little bit. Lots of different information here, but when we get to Ethernet, remember that was our layer 2. The destination is a Dell, and the address here. And we have all of the bits that are set, and they're set for zeros, and the source with its, and the destination, just like we said, that will be the destination, and the Ethernet's going to be first. And the address, the ARP reply says the hardware type Ethernet 1, Sender MAC address, Hisense, it's got here the sender IP address, the target MAC, the target IP. So it's sending its MAC address back to the requested. I just go down here and look at see more ARPs, and ARPs just go on and on and on. They don't stay in cache very long. Each of the operating systems is a little different. I think Microsoft's like maybe 90 seconds or something like that. If you use it, it stays longer. It kind of gets refreshed. But if we go to HTTP, there's going to be more information. But you can get this, run it on your own network. Just kind of look at what is in it, and we'll talk about. We'll get in here flags. We'll talk about a lot of this stuff when we get to the IP and the TCP portion of the course.
So each one of those lines was a packet capture?
Yes. Yeah, it's amazing if you do it, and that's for like, I don't know, probably less than a minute. It's just amazing how much traffic is on a network. I'll go back here. These are the times, and you can see 13, 17, 20. Let's see how far, if I can find the drag, how long I had it up. 120, well, I'm up 167 seconds. And you got that much information. In my network, it got like 4 computers on it. So you can imagine what a busy network would be like. You got to learn how to use these things. You got to learn how to filter these things so that you know what you're looking for, so that you can find what you're looking for. Okay. More questions and then we'll do labs. How's that? What is attenuation?
Attenuation.
I'll help, since somebody actually spoke up. So it's the loss of signal. Remember the car coming off of the mountain and without a gas, where you slow down? That's just my stupid way of remembering it. But attenuation is as you go down the copper, the signal weakens. True or false, digital signaling is typified by sending a stream of discrete pulses. This is a 50-50-90. You know what 50-50-90 is?
I think that's true.
50-50-90 is you get a 50-50 chance you'll screw it up 90% of the time. Well, I hate true, false.
It's true too.
I think it's true.
That is true, yes. And when you're doing true, false, unless you know why it's false, the rules say to mark true. What are multiplexing and demultiplexing? It all do that one. It means sending multiple channels on a circuit at the same time. I'm sorry, somebody was going to ask a question. Why might the baud rate be different from the bit rate? The baud rate is the symbol change measured in hertz. The bit rate's the amount of data that we do in these things.
I should know that.
CSMA CD, what happens if the computer data transmit and there's already data on the cable?
Get a collision.
Happen if a computer has data, I'm sorry, yeah, they would have, if it did transmit, there would be a collision. If it has data to transmit, it'll wait until it's off the line. I read that wrong. MTU is maximum transmission unit, the amount of data that the frame can hold. The CRC mechanism allows for the retransmission of damaged frames, true or false?
True.
Seems like a trick.
It is a trick, it's false. The retransmission happens at the transport layer.
CRC just identifies it.
CRC just says there's something wrong with it, and it says, oh, sorry, I can't use that, throws it away.
Oh, okay.
No request for retransmission. We'll get to that when we start talking about connection oriented. Yeah.
It's just a check. It's just saying.
Just check.
Okay.
Yeah.
Okay.
Which Ethernet standard uses coaxial cabling?
10100 base X.
10 base 2 and 10 base 5.
It's
10 base T is going to be twisted pair, the T for twisted pair, obviously. Okay, so I think we're just about on time for what I think I want to do. Have you done the introduction to the lab yet? What I would like to do, when you start the labs, there's going to be an intro lab, which kind of teaches you how to use the virtual machine. And then there's going to be lab 1, which is a 15-minute one, I think. I'd like to do those 2 labs tonight, and I'm going to be here until midnight, 10 your and 11 your times. But work on those. You should have a link to the labs. Now I have a question, and this is the survey. And if you don't vote, you don't get a say. But tomorrow we have the option of doing about an hour's worth of labs at the front of the course or at the back of the course. So I can start with lecture or I can start with labs, and I'm going to let you guys tell me what you want to do.
First off, where's the link?
Should be in your email. It's lms.leaderquest.net.
Let's see. She just resent it.
I prefer doing the labs later
Okay.
because I start losing focus and it wakes me back up.
I agree, and I've always done my classes, get the lecture at the front end when you first get there. Hopefully everybody's still awake. And then do the labs for the rest of it. So unless anybody objects, we'll do lecture first and then lab at the end.
Sounds good.
I hear no objection.
Is there? Well, I was gonna ask. Is there any way we can kind of like mix it up, like after each portion of the lecture, just kind of
They kind of
jump into a lab?
They kind of go to no, each one. We'll get more, but each one don't have labs yet.
Okay.
Uh,
Okay. Yeah, I think
one
that
of the
would be kind of nice
things
to kind of.
one of the things that helps, I think, sometimes is the immediate following material sometimes make the previous a little bit clearer, and then maybe the labs will bring it all together. Did you find the link?
Yeah. Now I'm trying to get in.
Okay. I can't help you. I can get you there, I think. lms.leaderquest.net, right?
Yeah.
So all I see is pre-class preparation, and then
Say again?
well, I see pre-class preparation at the beginning.
Yeah, that's the one. That's the one. That's a kind of a basic lab, and then the first one, I think, is actually configuring a network adapter, which many of you probably already know how to do.
So for the, it says test virtual lab environment, vSphere launch test lab.
Yep.
That's the one you want?
That one, and then the first one under there, you're going to have some. Let me see if I can get to it.
The configuring network. Well,
Configure
so
that.
that's just that's the orientation one.
Yeah, the orientation one's the first one, and then the configuring the network adapter is the first actual lab.
That do you want us to do?
Yeah, well, you're going to have to do all the labs before they're going to give you the voucher to take the test. And
well, I was talking about tonight. I'm not going to take them all tonight.
huh? No. We're going
to
to do the here's how the thing works, and then the lab one, the configuring network adapters. That's the only ones I want you to do tonight.
I don't think I have the lab.
lms.leaderquest.net.
I just posted a link right into the chat.
Okay, good.
Those are the directions right there. Use your email address.
Yeah, okay.
There's the password.
Yeah. Everybody see that? Username's your email address. PA $W0RD, which, by the way, is the password for all the labs too. When you have to log into
Can
them.
you hold on for just a second? I don't have the email either.
Okay, LMS.
Which is not unusual given.
Yeah, but
I mean, my other two classes, we never got the labs until the second.
It's okay.
LMS.leaderquest.net is the web.
What is it?
LMS.leaderquest.net. I got that one right, didn't I? For those of you who are there.
The link that I was given was lms.learnondemand.net.
That's right, Learn on Demand. Thank you. LMS.learnondemand. I see. I don't even know where I'm going.
I posted it right there in the chat. Everybody can see it. It's got a hyperlink. All you got to do is click it.
Oh, yeah. There it is. Yeah, it's in the chat. It's been posted. Who did that? Thank you. Just click on it, and that'll take you there, and then log in.
I get a bad host name.
Bad host name or certificate?
Okay.
I got this, which, man, that's the correct ones. I'm just going to go ahead and go there. That usually means there's something wrong with it. Well, that didn't go there, did it? LMS.learn on demand. There it goes. So you're going to log in here with your email address once you get there, and capital PA $W0RD for the password. Once you get there, go to the class. So I can do it on my calendar.
Can we hold up just a second? I'm not getting these labs by that link.
Did you, where do you go? Did you log in?
Well, into this chat, double clicked, and it says bad request, invalid.
You shouldn't have to. You shouldn't have to double click. You should just have to click on it, and it should open your browser. Then type into your browser address lms.learnondemand.net, or you can copy that, copy and type it, or copy and paste it.
Bad host name.
lms.learnondemand.net.
Yep. Bad host name. It sure would be nice if
Where are you
these
getting?
folks,
How are you getting bad host name?
I don't
Works
know.
fine for me.
No, but host name, they should have. You're not going to get a bad host name. You should get an HTTP error 104 or something, 404 if it's a bad address.
Yeah, the same crap until I deleted the backslash and the period.
Let me do something here. Let me get in Firefox instead of
Okay,
Google Chrome.
I have mine's there. Do you see the? I'm gonna be admin, but see the address that's in my address bar here. You may just want to type it in. Yeah, he's right, because there is a period at the end of that, and that won't work.
Just delete the period and the backslash and it'll load up just fine.
Yeah, I don't see.
Oh, this thing gets frustrating as hell.
I see. I'm gonna send you one that doesn't have the period and see if it'll direct link.
I'm in there.
Okay, good. Good. This is where I start to get confused in there.
When I click on configuring a network adapter, it takes me to G554 CompTIA Network Plus. And then I click that and I get a list of labs. Lab 00 update, yeah. Lab 1.
Lab 1's one you want to do.
But it says new lamp and router VHDs.
Wait. Let me get.
I don't know.
Let me find class. Yeah, because they actually have two.
I did that token. You have to do that token too, right? You have to do. I have successfully launched a lab. And that launch test lab was weird. There's ESX connectivity check.
Yeah.
So it's a VMware thing.
Oh.
Yeah, VMware is
All right, so then there's a series of just you check 1 through 10 display menu and all that, right?
Yeah.
That's the menu.
Yeah. Yeah.
So if I exit that, cancel my lab cancel.
Yeah, and if you don't finish a lab, you can save them, and I think it saves them for 30 days. If you cancel it, it starts you over.
Oh, now I got a different view after I said I viewed the lab. Now I have a launch here.
Okay.
Now I'm actually in the lab. Okay. Wow. I had to play with it.
Yeah. This is the one, if they have you do the Linux one, and I had some issues with it, after you make the changes, now it's later on, but after you make the changes, it said to control O, I think, to save it, but it didn't work. If you just did control X, it'd save it and exit.
This page. What the hell's going on?
It takes 2 minutes to build a lab.
Oh, I know, because it builds virtual machines, a set of virtual machines every time you start it. Unfortunately, and they all do it that way. Unfortunately, it can't save them. It'd be nice if you just built your set and left it, but it doesn't.
Too much resource.
Well, yeah,
so we'd
exactly.
have to clean out. So we'd have to clean it out after we leave.
Well, they wouldn't have enough resource to actually leave them all. Can you imagine the storage?
End up with the sand.
Yeah, at least. Because
I'm going to be quiet. I'm going to do my lab.
Okay.
I finished it. Are we good for the night once we do the lab? Larry?
Hello? Yes.
Are we good for the night once we finish the lab?
Yes. I think I tripped over my cord. Sorry.
Alrighty, thanks.
Have a good evening.